for the people who aren't here, we started our lab 2-2, and we have weighed a little piece of metal, and we're heating that up in a pot of boiling water, and you should remember that boiling water is 100.0 degrees Celsius. All right, so last week we talked about converting from Fahrenheit to Celsius, from Celsius to Fahrenheit, and also from Celsius to Kelvin. So make sure you know how to do all those conversions. One other thing that you need to know is on page 48, 1 calorie is not the same as a food calorie when you're eating your Snickers bar. This is a calorie is a measurement of energy, and it's also 4.184 joules. And we are going to measure most things in here in joules. It's just a measure. It's a unit of measure. A unit to measure energy. Okay. So so that equals 1 calorie small c. If you are talking about the Snickers bar that you ate, that's actually 1,000 small c calories equals 1 food calorie big C. There you go. So when you're eating your food, it's measured in calories, but they're different calories, just so you know that. It's 1,000 times bigger. Okay, so we're going to be talking mostly about joules. And today we're going to be talking about something called specific heat. Specific heat. The specific heat of something is the amount of heat that is necessary to raise 1 gram of a substance, so 1 gram of water, 1 gram of metal, 1 degree Celsius. So it's raising 1 degree Celsius if you have 1 gram of that substance. And there are charts that measure the specific heat of things, so they have figured out the specific heat of pretty much every substance you'd ever want to know. So on table 2.1 it has copper, it has iron, it has glass, it has aluminum. Probably we're going to be figuring out the specific heat of the metal that we have. We're going to calculate that, and then we'd be able to look on a chart and see what that kind of metal is. If we had really great ways to capture the heat, and we learned last week that our thermometers aren't super great and accurate, right? So if everything was accurate, we would be able to very easily take the specific heat that we calculate and then be able to tell what kind of metal it is. Because we could go to a chart, we can look it up on Google, look up the specific heat of a certain amount and be able to figure out what that item is, which is kind of what you're going to be doing in your lab. You're going to figure out the specific heat, and then you can use this table if you want and just say it's closest to glass, copper, whatever. It's probably not going to be exactly these, but we measure it in joules per gram degree C. Why? Because specific heat is the amount that it raises the temperature 1 degree C, 1 gram of that material, and it's taking into consideration how many joules of energy that takes. So you're going to want to remember the specific heat is joules per gram degree C. Lost my eraser. Okay, so if the specific heat is joules per gram degree C, you're going to know that all of your temperatures that you're taking are going to be in Celsius, right? Because you need that to cancel out. Okay, so how do we figure that out? Well, the specific heat is, because there needs to be more letters in the alphabet, but there's not. So the specific heat is the C. So C is for calorie, but usually they write CAL for calorie. but this is a small c, and that's what they use for specific heat. So we can also measure the change in temperature. The way we're going to figure out the specific heat is by a formula that is Q equals mc delta T. Okay, what does that mean? Well, Q is going to be the heat, so we're going to have a little pot, we have boiling water in there, we put our little metal in there. Q is going to be the heat that is in the pot. So if something is giving off heat, it's going to be negative Q, and if something is gaining heat, it's going to be plus Q. Okay, so Q is just the heat. Negative means it's coming off, positive means it's going in. So right now, our metal is not very hot, but the water is. So the water is giving off heat, right? So it's got a negative Q, and that metal is gaining heat. And in a little bit, we're going to take that metal out of there. We're going to put it into a very scientific calorimeter, in other words, a styrofoam cup. And that metal is going to go into the water, and some heat is going to come off of that metal and go into the water, and we're going to measure that temperature change, right? So the Q, the heat, is coming off of the metal, so negative Q coming off of the metal, and it's going to go into Q that goes into the water, positive Q. Now the same amount of heat that came off the metal is the same amount of heat that's going into the water. So Q is the same. The sign is just showing you, is it coming off of it or going into it? Does that make sense? So the same, this Q is the same, okay? It's just, this is a positive because it's going in. So your temperature is going to raise a little bit, assuming you can measure that. Maybe it's gonna, get 25 degrees warmer. But we're gonna put a hot piece of metal into some water, and your water should raise a little bit because you're putting a hot thing in there, right? So your heat comes off of your metal and goes into your water, and we're gonna measure that with our very accurate thermometers, and you're gonna see how much your temperature changes. Okay, so delta T then is your change in temperature. How do you figure out your change in your temperature? Well, you measure your final temperature. Let's say your final temperature is 27 degrees C, and you subtract your initial temperature. Let's say it started out as 25 degrees C. So 27 minus 25, that means the change in temperature would then be, math is super hard on this, 2 degrees C, right? So your change in temperature would be 2 degrees C. We'll see how much yours changes when we get over there. But just so you know, your delta T in this equation is change in temperature, okay? All right, so we've already discussed that C is your specific heat, and we are gonna solve for C this time. But usually, when you're doing a problem, they're gonna give you the specific heat. They're gonna tell you this is iron, they're going to tell you it's copper, you're going to go right to this chart on page 50, and you're going to get your specific heat from there. Your M, because we've had big M for molarity and molality, so here's another M, and this M is going to be your mass. So you all weighed your little metal piece. What was your weight of your metal piece?
42.01 grams.
So M is going to be 42.01 grams. Okay, so that's going to be your M. So what we're going to do is we're going to figure out how much our temperature changes in our cup. And so let's say that'll be about 2 degrees C, that's in C. Your C is going to be what we're calculating. Your M is going to be in grams, so let's say that's 42.01 grams. Your Q is going to be the heat that comes off of your metal. So let's see. So we can, where have the, so you can figure out the heat that comes off your metal by how much heat was in your pot to begin with. So if it's, well, we'll get there. So we're going to use this in a minute. So let's do example 2.3 on page 51. Okay, in order to cook an omelet, remember we need Q, oops, I can't write, Q, M, C, delta T. In order to cook an omelet, a 5 kilogram iron skillet, so mass is going to be 5.0 kilograms. Iron skillet, iron means we're probably going to have the specific heat of iron. So we're going to look on table 2.1 to figure out what iron is, and that is 4.521 joules per gram degrees C. Must be heated from room temperature, 25 degrees C, to 150 degrees C. So that means my change in temperature, remember that's temperature final minus temperature initial. So in that, it was heated from 25 degrees C to 150 degrees C. What's the final temperature? Which one is the final one?
The one that's final, so
Which one?
150.
So it ended up being 150.0 degrees C. That means it started out at 25.0 degrees C. So if I subtract those, I'm going to get 125.0 degrees C. So I could write that here, 125.0 degrees C. And it says how many joules of heat must be used to accomplish this. So I'm figuring out my Q, because that's always going to be your joules. Okay, so remember Q equals MC delta T. And if you set it up right and you write everything out, and you don't necessarily have to memorize joules per gram degree C because it's given to you in your chart. But if you set everything up right, all your units will cancel out. Okay, so we're solving for Q. So, and this is in joules per gram degree C, so this isn't in grams. We gotta first convert that to grams. If you don't remember how to move your decimal, I want my kilograms to cancel out, and I want grams to go on the top so that, and this has to be a true statement. And there is 1,000 grams and 1 kilogram. So I'm going to multiply 5 times 1,000. So I have 5,000 grams, was my M, times, they told me that it was iron, so 4.521 joules per gram degree C. I got that from a chart. And my delta T is going to be 125.0 degrees C. Now before I go too far, this, how many significant digits are there? Anybody know?
2.
2, very good. So non-digit zeros are always significant, and then this goes past the decimal, so that means that's not a placeholder 0 anymore. That means I measured to that place. So I didn't write this with the right significant digits. I'm just lazy. So I just need to remember, maybe put a line under it or over it. There's only 2 significant digits here. This has 4, this has 4, but because I only have 2 here, I only get 2 in my answer. Okay? So, if you put your calculator then, so how many joules of energy does this take? I take 5,000 times 4.521 times 125. So that's a lot. I get a Q of 2825625 joules, but I only get two significant digits. So this is the only one that's significant. So I have to look at this place and say, is it 0, 1, 2, 3, or 4? I round down, which means I round to 28. If it's 5, 6, 7, 8, or 9, I round up. So it rounds to 2, 8, and then these are all just placeholders. 1, 2, 3, 4, 5, 6. Oh, actually, maybe I did something wrong. 5,000 times 4.521 times 125. 1, 2, 3. I got one extra digit here. Correctly. My calculator is running out of batteries and not working great. Times 4.521 times 25. I don't know, I still get, I don't know what I'm doing wrong. 280. They have in the book 280, so I have an extra digit here, 1, 2, 3. But I don't know how I'm getting that wrong. 5,000, right? Times 0.452 times 125. I don't know what I'm doing wrong. So I'll figure it out later, but it'll be too late. 5, I'll do it one more time. Otherwise I'm gonna change my calculator. 4.521 times 125. I'm getting 2825625. Anybody else have a calculator? Maybe my calculator needs to.
I think it's supposed to be 0.4521.
Do I have my decimal wrong? That's exactly it. Thank you. Candy for you. That would make a difference. Thank you. All right. So, still has two significant digits. That makes a difference. Okay. Use the right numbers, you get the right answer. Nice job. So, that's a lot of energy. So when you're cooking your eggs in the morning, you're heating up your stuff a lot. A lot of energy is going into produce heat, okay? So remember, specific heat is the amount of energy used to raise 1 gram of something 1 degree. So you have to get it really hot if you're cooking your egg. All right, let's do another one. I need Q, M, C, delta, T. 304 gram mass of copper, so that's 305.4 grams of copper. So go back to your chart, point 3851 joules per gram degree C. Is initially at 75 degrees Fahrenheit. Oh, do you see a problem? 75 degrees Fahrenheit. Dang it. We don't want it in Fahrenheit. We have to convert it to Celsius. It is given, this is final. No, this is initial. So this is temperature initial. And so this isn't actually your delta T. You still need temperature final. Is given 1, 2, 3, 4 joules, 0.0 of energy. What will its final temperature be? So now I want that. Ugh, what a disaster. So first, I know we have to convert my Fahrenheit to Celsius. How do I do that again? Well, degrees C equals 5/9 times your Fahrenheit temperature minus 32. And remember, you have to work inside your parentheses first. So you're gonna write 75 minus 32. 75 minus 32 is 43 times 5 divided by 9 equals 23.88888888, and this is the number that I'm basing my significant digits on. I only have 2 here, so I'm only going to have 2 here, which means 23.8 gets rounded to 24 degrees C. Okay? So that's going to be here. Your temperature final is 24, your temperature initial is 24 degrees C. All right, so now we go back to our fun Q equals MC delta T. Doesn't that just roll off your tongue? It's so much fun. Okay, but what do we want? We're going to solve for delta T because we need to get it into to figure out their final temperature. So I'm going to divide this side by M and C, which means I divide this side by M and C. So I have Q over MC equals my delta T, because that cancels, that cancels. Okay, so that equals 1234.0 joules over my mass, 305.4 grams, times my specific heat, let's get that right this time, 0.3851 joules per gram degrees C. So this gram cancels that gram because they're multiplied, and that's on the bottom of the fraction. This joule is on the bottom of the fraction from this joule, so that cancels. So I have a degree C that is on the bottom of a bottom fraction. When dividing fractions, don't ask why. You ever do this with Mr. Demi? Flip the sucker and multiply, right? So what happens to that degree C? It flips up. So my unit, my final unit, is going to be a degree C. Okay? So that's how I know that I'm setting it up right, is my units are canceling out. I have kids who don't like to write, and so they just skip all the units. But if you take the time to write your units, you can see, did you set it up right? Because your units will cancel out. So that cancels that, this grams cancel that, and your degree C flips up. So, 1, 2, now this is an order of operations problem. If I do 1, 2, 3, 4 divided by 305.4 times that, it's not going to work out. So, because what you're really doing is taking this divided by this and then timesing it by this. So that won't give you the right answer. So what you might want to do is do this times this first, get an answer, and then do 1, 2, 3, 4 divided by that. Or learn how to use your parentheses, which I like to do because I'm super lazy. And I will do 1, 2, 3, 4 divided by parentheses, this times this, end parenthesis, then hit equal. If you set it up, but you put it in wrong, and you have an order of operations problem, but I can see that you set it up right, I will still give you most of your credit, because it's just an order of operations problem. So, I would do 1, 2, 3, 4, divided by parentheses, 305.4 times 0.3851, end parentheses equals, I should get, good, I got it right, 10.49236, blah, 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 blah. How many significant digits do I get, though? Well, this has 5, this has 4, this has 4, so I get 4. 10.49, I look at the next one, do I round up or down, and it just falls off. And my unit is degrees C. So am I done? No. Because this told me the change in temperature. I just solved for delta T. So then I have to go over here and solve for this. If I have my change in temperature equals my final temperature minus my initial temperature, which was 24 degrees C, I'm solving for this. So what you can do is when I have a number here that's my delta T is 10.49 degrees C equals my final temperature minus 24 degrees C. So I can just add this 24 degrees C to this side, add 24 degrees C to this side, and that will solve for my final temperature. You see that? So that this cancels out. So my final temperature is going to be 24 degrees plus 10.49, but when I'm adding and subtracting significant digits, I'm going to round to my least significant place. So that means I'm rounding to this place. So what's 34.49 degrees C? Rounded. This is 0, 1, 2, 3, 4. It falls off. And so my initial or my final temperature is 34 degrees C. This is why we don't do this at the beginning of the year, because you're like, I hate chemistry. I have no idea what's going on. There's too much math. What's the point? Because this is actually not the longest problem. Don't want to be a Debbie Downer, but it's not hard math, but there's a lot of it. So if you remember, Q equals MC delta T, and you set things up, you will do very well. But what we're doing today is what we call calorimetry. Again, our calorimeter, just for the people who aren't here, is this very scientific calorimeter here. What does a calorimeter do? It measures how much heat is coming off of something like the metal that we're putting in. A real calorimeter would have a cover on, and it would not absorb any of the heat in itself. And all of the heat that comes off of the metal you put into your water would go into your water, so you can measure very accurately how much heat has gone into your water. Is our calorimeter going to be that exact? No, it's not. Because some of the water is going to be absorbed by the calorimeter. Some of the the heat is going to be escape out into the atmosphere. So this isn't super accurate, obviously. Okay, so that's why we usually use charts when you're wanting to find that. You would know what metal you have, and you would find it from a chart somewhere what your specific heat is. If you don't know your metal, then you would do something like this, and that's how they discover what kind of metal they have, sometimes. So, but that's what a calorimeter does. So, the specific heat of water is always the same. It's 1,000. I'm sorry, 1.0. 1,000. Just because I can. It's 1.000 because it's measured to that spot. Calories per gram degrees C. Is that important? Yes, because the specific heat is how much, but we're learning how many joules. So how many joules is that? It's also 4.184 joules per gram degrees C. I don't remember on your test if they give you this number, but if you do your problems in your chapter, you use it for every problem, and so you'll have this memorized. But so just know that it's 1 calorie, but it's 4.184 joules per gram degree C. You probably haven't used joules very much in your life, but again, it's just a measure of heat, okay, energy. So they showed on page 54 how they set up a calorimeter. And remember I said that when we have this, the heat that comes off of something is your negative Q. So there's going to be heat coming off your metal, and there's going to be heat going into your water, and that's positive Q. So there's another equation that is negative Q from your object is going to equal the Q, the water, the energy, the heat that goes into your water, plus the Q that goes into your calorimeter. Right? Does that make sense? So I'm going to drop a little metal in here, and the heat is going to come off of the metal, and it's going to heat up your water. And like I said, this isn't a super high-tech calorimeter. It's also going to absorb some of that heat. Some of the heat's going to also escape out. So most of your questions, when they're nice to you, they're going to say ignore the calorimeter. Yay! So the heat that comes off your object is the heat that's going into your water. But at least one of them on your test is not very nice, and they say you also need to figure out the heat for the calorimeter. Boo! So that is a super long problem, just warning you now. But it's not any harder, it's just adding one more thing in there. And the reason we can usually discount the calorimeter is because when we round our numbers, it usually falls off anyways, because usually we only have one or two significant digits. So let's do example 2.4 after I let my dog out. So it's not loud. All right. I want to give you enough time to do the lab, so. A chemical reaction is carried out in a 5-gram calorimeter. The calorimeter has a specific heat. Okay, so now just remember, you're going to have a Q equals MC delta T for the water. You're going to have a Q equals MC delta T for the object. And you're going to have a Q equals MC delta T for the calorimeter. Boo. All right. So the calorimeter, when I'm reading the question, I write down so I don't get confused what numbers go where. Chemical reactions carried out in a 5-gram calorimeter. So we're talking about calorimeter, MC delta T. So it's a 5.0 gram calorimeter. Calorimeter has a specific heat of 1.95 joules per gram degrees C, and it's filled with 150 grams of water, MC delta T. So my mass of water is 150.0 grams. If the temperature of the water was 24 degrees C, remember that's temperature final minus temperature initial. So it was 24 degrees C, and it rose to 32 degrees C by the end of this experiment. How much heat was released in the reaction? All right, so remember, I should have put them in a different order. So your Q, what's happening? You have this object, but again, this isn't really an object now, it's a chemical reaction, some chemical. Gave off some heat, so negative Q. And what did that heat do? It went into your Q for your water, and plus your Q for the calorimeter. Right? So this reaction took place. It gave off heat that went into the water and the calorimeter. All right? So they want to know, what is this Q? Okay, well, to figure that out, I need to figure out the Q for the water, and I need to figure out the Q for the calorimeter, and I need to add them together. So it seems like a lot of steps, and it is. So I'm going to erase object and I'll say of the reaction. But just so you know, in your formulas in your book it says Q of the object, but in this case it's the reaction. And remember, this negative here just means that that's where the heat is coming off. It's going to be the same Q's that are adding together to make that, okay? So let's figure out the Q of the water. Do we have everything? Q equals MC delta T. Well, I don't have the C in the question, but they told me before that the Q of water is 4.184 joules per gram degree C. Okay, so if I set that up, I have the Q of the water to be M 150.0 grams times C 4.184 joules per gram degree C times delta T, which it started at 24 and it ended at 32, so my change in temperature is going to be the difference between those. So 32 minus 24 is 8 degrees, and I round to the least significant place, so it's still 8 degrees C. So see what happened? I only am going to end up with one significant digit. So actually they gave me 2, only because it's 32. I was too lazy. 32.0, 24.0. All right, so I get 2 significant digits. All right, so what's the Q of the water? 150 times 4.184 times 8. The Q that's going into the water, the energy that's going into the water is 5. Just double check that I didn't make a mistake again. Yeah, 5021 joules. And I have 4 there and 4 there, but only 2 there, so I have to round it to this place. So that falls off. So 5,000 joules went into the water. All right, so let's figure out how many joules went into the calorimeter. Well, they didn't tell me in the question that about my delta T, but if you have a calorimeter and water sitting there, like this one is, what's my initial temperature of my calorimeter? It's going to be the same as my water. What's the final temperature of my calorimeter? It's going to be the same as my water. So if I figure out that delta T, unless they tell me that it's different, I'm going to assume it's the same. So I'm going to figure out that is going to be 8.0 degrees C too. So can I figure out the Q of the calorimeter? Yes, I can. It's going to be, Q is going to be MC delta T. So it's going to be 5.0 grams times 1, I don't want to get my number wrong, 1.95 joules per gram degrees C times 8.0 degrees C. So this gram cancels that gram, this degree C cancels this degree C, I'm left with joules. So the Q of my calorimeter is going to be 5 times 1.95 times 8, 25088. 5 times, why did I get that wrong? 5 times 1.95 times 8. Oh, I don't know where that number came from. Okay, 78 joules. So how much heat came off this reaction is going to be the Q that came off the reaction is going to be the Q from the water and the Q from the calorimeter. So it's going to be 5,000 joules that went into the water and 78 joules that went into the calorimeter. But here's the problem. I only get 2 significant digits here, so when I add the 78, does it even matter? No, it doesn't. So they made me do all that work for nothing. Well, I guess. It ends up being 5078, and I have to round to this significant digit, so it rounds up. I guess it rounds up to 5100 joules. Okay, eventually, some of them they just cancel off, so that's why they say ignore the calorimeter. Okay, so am I done? Well, the problem said how much heat was released. So is this how much heat is released? Yes, it is. So it's in joules. So that's a negative Q, so really it's negative because it's coming off. Did I lose anybody? Is this fun? This is why we didn't do this at the beginning of the year. You'd all given up on chemistry on me. So that's how much heat came off of the reaction. Okay, well we learned in the last problem that frying an egg was 280,000 joules. So is it a lot of heat? Not really. So would you feel it? I mean, probably. You'd say it was an exothermic reaction. You'd say some heat came off. But I don't know that it'd be enough to cook anything. Okay? All right. I don't know that we're going to have enough time to do another problem. They're all similar. The hardest thing is figuring out when they're giving you numbers in your question, what are they talking about? Are they talking about water? Are they talking about your calorimeter? Are they talking about your object? Figure out what they are, write down what you know, and solve for the things you don't know. And when they say ignore the calorimeter, say yes, and just skip that part, okay? So then you can know that your Q of your object, the negative Q is going to be the Q that went into the water. Okay? So, all right. So what we're going to do now is we're going to drop that hot metal into your calorimeter. You're going to watch and be shocked at how much your temperature is going to raise. It's shocking. And then you're going to figure out your Q equals MC delta T. You should know the C of water, and you're going to ignore the calorimeter. So you're going to have to figure out your delta T, which is going to be, you have to read your initial temperature first, and then you have your final temperature is how much it raises to figure out your delta T, you know, your mass of your little rock, and you're going to figure out the Q that comes off, okay? And then you're going to be able to figure out the C. The goal is to figure out what the C is for your stone. Okay? All right, so we'll work that together if we have time once you figure out your temperature change. All right. So I'm going to put this hot thing in there, and you're going to give it just a minute, and then you're going to stir, and then see how much your water temperature raises. Did it go up at all?
No.
No? Look carefully. See if it did. It should have gone up maybe a little bit. So Q of your...
Maybe like 2 degrees Celsius or something.
2 degrees. 2.0?
Sure.
Look carefully. So we have Q equals MC delta T. And Q equals MC delta T. So so this is your object. So we're going to have, how heavy was your rock?
42.01 grams.
42.01 grams. So we don't know the specific heat of our rock. And so what is our delta T gonna be? Let's figure out the delta T. It's gonna be the temperature final minus the temperature initial. What was the initial temperature when we dropped it in there?
The rock.
Uh-huh.
100.0 degrees Celsius.
100.0 degrees C, because it was in boiling water, so we know that the temperature is 100. Okay, what's our final temperature of the rock now?
About 22 degrees Celsius or so.
22 what?
Um,
You didn't write any of it down? You're just doing this out of your brain?
yep.
Did anybody write it down? What's the temperature of the water right now?
22 point something.
Yes, point what? Tell me what it is. 22.0. Okay, so our delta T on our rock changed a lot. So it's going to be 22 minus 100. It's going to be a negative 78 degrees, point zero degrees C. Okay? Wow, that was a big change. Negative 78.0 degrees C. You see why negative? Because that's the heat that's coming off. There's where your negative's factoring in. Okay, so we're going to have to solve for C here. So we don't know quite yet what this Q is. How do we figure that out? Well, the negative Q of the object is going to be the same as the Q that went into the water. You could be writing all this down. Or you can take a snap picture of it later, because this is really your results. Okay? So the Q of our water, did we weigh our water? Probably we're going to have to go back and weigh our water. Take the little metal out and weigh our water. So we're going to need our grams of our water. Do we know specific heat of water?
100 degrees.
Close. It's 4.184 joules per gram degree C. What's our change in temperature of our water? What was our final minus initial? What did it start out as? What did our water start out with when it was room temperature?
Like 20.0 degrees Celsius.
20 what?
0.0.
20.0 degrees Celsius. And what is the final temperature of the water?
22.0.
22.00 degrees C. So our delta T is going to be 2.0 degrees C times 2.0 degrees C. So we still need to know how many grams of water we have. So here, let's take this out and weigh it. All right, so the weight of your water is Get it? Can't figure it out?
Okay, so the calculated,
You can use a calculator. Totally don't mean you do that in your head.
No, I was trying to get it.
Okay.
Wait. So this calculated 4 grams, so 4.00, I guess, because it was like on 4. And the watt, this whole thing weighs 189.83.
189.83
So
minus 4.
4.00.
4 grams equals, my grams is 185.83 grams. Okay, so we're gonna take 185.83 times our C times our delta T. We're gonna get a Q of times 4.184 times 2, 1555 joules. This has five, this has 4, this only has 2. So I only get 2 significant digits, but this is a 5. So it's gonna round up. So 1600 joules went into the water. That's how much joules came off of my object. So it's going to be, this is positive, went into my water. So it's going to be negative 1600 joules that went out of my rock. And so I just rearranged my Q equals MC delta T to solve for my C. So I divide that by how many grams my mass was of the rock, times negative 78, because that's the change in temperature. So I'm going to do 1600 divided by parentheses 42.01 times 78 negative equals, so I'm going to get a C of about 0.4882, I guess 4883. I only get 3 there. I got 4 there. I only got 2 there. So 49, and it should be joules per gram degree C. And so you're going to look on your charty chart and say, what's our metal? I forgot what page our chart was on. So is that close to iron? Iron is 0.45. This is 0.49. Could our metal be iron? Probably. So I'll send you all this video, or snap a picture of this. This is kind of going to be your results. You're going to want to tell me what your specific heat ended up being. You're going to want to tell me what metal you guess it was. But really what I want you to do is practice writing this so you understand Q equals MC delta T, and practice doing it because the test is kind of long. So get the hang of doing it. Okay? Okay. If you have more questions, you can email me, but that's as evil as I want to be to you today. Okay?